enough, if I know that the curl of the vector field is 0, does it automatically then follow that there exists some function phi? See, that's a stronger thing, right?
Well, presumably, if you allow for your function phi to be trivial, where it's like equal to 0 or something, that doesn't matter. If you have e equals to 0, 0, 0, I mean 0.
The answer turns out to be no. But sometimes yes. That is one of those things we need to understand. It's a subtle, it's probably the most subtle point in this part of the course. The converse to that condition, like the when curl being 0 is enough to show you that there's a gradient for the vector field. By the way, this is sort of an annoying thing to keep saying, when there's a gradient to a vector field, when there's a gradient to a vector field. So this is a definition for us, guys. Definition, F is a conservative vector field on U, which is some subset of Rn, all right? If and only if there exists phi, which is some function from U to the reals, with f equal to the gradient of phi. Yep.
Does that have anything to do with conservative forces?
It does. In fact, everything we're studying here is a force field,
Got it. Okay.
which makes all of this awesome. Because we all wanted to think about force fields when we were kids, right? Now I'm showing you the tools. But yeah, it's a conservative vector field would be a conservative force if it has the interpretation of force. But of course, the concept of vector field doesn't, I mean, every vector field doesn't have to be. Exactly, it could be a force, but it doesn't have to be. So we've got gradient, we've got curl, we've got divergence. Now, I have proved for you some of these things, but I think your patience grows thin with me proving all of them. I think I proved it enough that when I show you the remaining proofs, you should be able to make sense of them at least, right? You should understand my notation. I think I've hopefully gone over enough of it. Let me show you some more, though. If you were so foolish as to calculate the divergence of the cross product of two vector fields, right? You could take two vector fields and calculate their cross product, right? You could do that. That would give you another vector field. It turns out that that has, it's g dot the curl minus f dot the curl. That minus is perhaps surprising. If you calculate the gradient of the dot product of two vector fields, that's also making sense, right? Because this is a function, so you can calculate its gradient. That works out to f cross the curl plus g cross the curl plus f dot del g plus g dot del f.
Right.
This is not at all obvious, right? This is a notation for an operator. This is like f1 partial partial x1 plus f2 partial partial x2 plus f3 partial partial x3, right? So that acts on g. And then, of course, the gradient. Well, I think this is missing. I'm missing something here. What am I missing? I think I'm missing a curl right here. This is the curl of the cross product is this animal.
Okay.
Yeah.
Yeah, that makes sense.
Now here's the proof for part one. I take the divergence. Here's the kth component of the vector field f cross g, which is epsilon I j k f I f j summed over I and j. But then this is just a constant, so you can pull it out. It's either plus minus 1 or 0. So you pull the epsilon I j k symbol out. It's just a constant. It doesn't depend on x, y, z. Then you got a product rule, and of course then you can rearrange the sums. The thing about it is the I and the k here, you have to flip. You start with ijk, but you have to go to ikj in order to make it a cross product over here. That's where the sign comes from. The epsilon is anytime you flip a pair of indices, you get a minus, because that's the same anti-commutativity which builds into the cross product and so forth. Oh, homework. Yeah, so I might give you a homework to derive the other two, or one of them. Would you guys like to do that homework? Nope. So the divergence of a curl is also 0. The curl of a gradient 0. We learned, we did that one, right? But this one's more fun. The curl of the curl is the gradient of the divergence, which this is, by the way, the Laplacian of a vector field. Oh, I'm sorry. No, it's not. That's the Laplacian of the vector field. So this notation means minus, this is partial x squared plus partial y squared plus partial x squared plus partial y squared plus partial z squared as an operator. That's what this del squared is. So like del squared, this del squared, turn on lights for just a second. Sorry. So you can take this Laplacian operator, and you can just as well let it act on a function like we did in this example. But if you let this act on a vector field, it still makes sense. That just means you take the Laplacian component-wise. So it's still like this is a meaningful statement up here. It says that you take the Laplacian each component of f. All right? Yeah, thanks. Now, we can look at the proof of this. But I think it's more important for me just to stop and talk about physics for a minute and show you the implication of these identities, because it's really interesting. So these are Maxwell's equations. Ultimately, your goal in Physics 232 is to understand these. But we're afraid to show these to students, so we changed these to ugly integral formulas, which is so sad. But this is the proper set of Maxwell's equations in the language of vector fields. Step on the direction, step on the path to the right ones. These are still kind of boring because I'm assuming that there's no charge and that there's no current in the space we're considering. If there was charge, this would be replaced with rho over epsilon naught, where rho is the charge density. If there was current, the curl would have another term over here, mu naught times J, where J is the current per unit area time, the current density. And this would be, so this is Ampere's law if you add the current term over here. It gives you the Ampere's law you learn in Physics 232. This is Gauss's law if you include the charge density over here. This gives you that charge enclosed over epsilon naught is equals to the flux of the electric field that you may or may not be studying in Physics 232 right now. This is Faraday's law. This one is the no magnetic monopoles, right? So we'd actually like to understand those things I just said as we go on in here. And I'll keep coming back to this example because it's kind of the central example in your education, so we should talk about it more. Yeah.
So, did we assume those things because they're things that normally don't exist? Or because they're things that they just don't decide to show you?
Oh, why, you're asking why we don't show those in Physics 232?
No, you said if we assume, and then you said some stuff that I...
Okay, so what I'm saying is the context of the Maxwell's equations here is that we're in free space where there's no charge and no current. So these are just Maxwell's equations in the vacuum, just out there without nothing, just free space. No charge, no current.
Aren't there normally charges and currents now?
But this is an ideal concept.
So ideally, in the vacuum. So then we can use this vector calculus that I've started to show you how to derive and so forth. If you calculate the curl of the electric field, right? That is the curl of minus the partial derivative of the magnetic field with respect to time, right? And on the other hand, it's this stuff here, right? It's the divergence, it's the gradient of the divergence minus the Laplacian of the electric field. Well, this is 0. And so the curl of B was what? It was the partial derivative of the electric field with respect to time. So a lot of these things, so basically 0, Laplacian of E, and this gives us the second time derivative of the electric field, which gives us this equation. The Laplacian of E is mu naught epsilon naught, the time derivative, the second time derivative of E, and this happens in each component. You guys have had physics 231, some of you? No? Show of hands, who's had 231 in here? So you guys talk about wave motion? Do you remember the wave equation? Did we talk about the wave equation?
I took it last semester.
Well, in any event, all of you will soon take differential equations. We should talk about the wave equation in there, at least if you take it with me, or if you take it with Scambortis. Oh, Scambortis hasn't been teaching a little bit, but anyway, this is a wave equation. So because we have the second derivative with respect to space is proportional to the second derivative with respect to time, this is the differential equation which a wave on a string satisfies, for example. This is the differential equation of a transverse wave. And the same thing happens for the magnetic field. And the really neat thing is the meaning of this coefficient has to do with the speed squared of the wave. So what this derivation I'm showing you seems to say is that the electric magnetic fields in a vacuum are waves, and that the speed of these waves is dependent only on the so-called permittivity and permeability of free space, mu naught and epsilon naught. This is really weird in some sense because, you know, and this in fact here, this v, 1 over the square root of mu naught epsilon naught is about 3.0 times 10 to the 8th meters per second. This is the speed of light. And this derivation shows you that electric and magnetic fields are naturally interpreted to have a constant speed that depends on the properties of space itself and not where the electric and magnetic fields came from. In other words, this is the discovery that electricity and magnetism is inherently relativistic. So when Einstein came along and he realized that there was a contradiction between classical mechanics and electrodynamics, he had a choice. He could either modify electrodynamics to make it conform with mechanics, or he could modify mechanics to make it conform with electrodynamics, or he could look for some middle ground. Turns out we didn't need to find a middle ground. Electrodynamics was already correct in terms of relativity with the proper interpretation. This is one aspect to that. I shut up anyway. Thanks, guys. So I'll not see you tomorrow because tomorrow is the very fascinating and exciting assessment day. Yay.